welcome. I just wanted to give a quick intro of Courtney. Dr. Courtney Hatch. She did her undergrad at Hendrix College, which she is now working from. And she did a PhD. She completed her PhD here at CU with Maggie Tolbert and went on to Iowa, I believe, University of Iowa, remind me, yeah, where she did a postdoc. And she's been at Hendrix College again as an assistant professor for the last 6 years. And yeah. And today she's going to tell us about water absorption on model atmospheric clay minerals and as a function of RH. So take it away.
Thank you. Can everyone hear me all right? Good. We're going to record properly. Okay, sure. So first, I just want to thank Becky for inviting me here today and showing me around. It's, of course, my visit wouldn't be possible without you and all the work you put into this. So I know it's a busy time of year. So thank you very much. And second, I want to apologize a little bit. I'm still getting over kind of nasty cold. So if I break out in a coughing fit, maybe I'll garner a little sympathy. So I want to talk a little bit about a couple different things today. The first, of course, I'm a scientist, so I like to share my research, and so that's first and foremost on my list. So I'm going to talk about some research I've done with my undergraduate students at Hendrix College. Some people have asked, what's Hendrix? It's a private liberal arts school in central Arkansas. So we have about 1,500 students, 1,500 students total. And three of the students that did all the work that I'm going to talk about today are Annie Greenaway, Josh Harris, and Matt Christie, and this work was funded by the National Science Foundation, the Research Corporation for Science Advancement, and the Hendrix College Odyssey program, and I'm happy to answer questions about the Odyssey program if you want to know what that is a little bit later. But I'm also here, the reason I'm here at NCAR and in Boulder is because I'm trying to develop a engaged learning project, and I've tentatively called it the eApproach program. And I'll tell you what that means a little bit later, but that's really why I'm here, is to kind of meet people and talk to people about what opportunities we could have for undergraduate students to interact with scientists in professional settings. And so I'll briefly touch on that at the end, just to give you an idea of why I'm here and who's funded my trip, of course. And so to make a long story short, what we do is laboratory work on really looking at easy ways to understand indirect climate effects of aerosols. We use really simple tools to measure water absorption on insoluble particles. In our case, we've used FTIR to measure water uptake on mineral dust. And using some more recent advances in CCN activation theory, we've been able to apply our experimental results, combining them with the theoretical calculations, and be able to predict CCN activities of mineral dust. So that's kind of really the exciting piece. And the punchline is that it works really great, at least for the systems that we've studied so far. And so it provides a very simple, cheap, and easy way to get at the CCN activities, or cloud condensation nuclei activities of dust particles. So that's basically what I'm going to talk about. So a brief outline. I know we're all probably familiar with aerosol climate effects, so I'll glaze over that a little bit. But I'll go into a little bit more fundamental science about how particles nucleate cloud droplets in the atmosphere, how that works. I know a lot of people I've talked to today do a lot of gas phase chemistry, so maybe they'll be less familiar with that. And I'll introduce some recent evidence for why pre-adsorbed water on the surface of these insoluble particles can affect the CCN activity of the dust, and how the evidence has led to modifications in traditional Kohler theory in our understanding of how insoluble particles become active cloud nuclei. And so these recent advances have really what's led to our experimental measurements. And so I'll show how we measure water absorption, and we've done it specifically on clay particles, and I'll explain why we look at clays. And then we apply our experimental measurements to this new new, what they've called the Frenkel, Halsey, and Hill adsorption activation theory. So it's a modification of Kohler theory to predict CCN activities and give you some results from that. And then again, I'll briefly talk about the eProach program that I'm trying to develop with my undergraduate students at Hendrix. So we've probably all seen this in a number of different iterations. IPCC plot of various factors that contribute to climate change and our current understanding of those factors. And we know that one of the biggest issues, or in terms of the lack of understanding, is how aerosols contribute to climate change. And that involves both the direct effect and what's called here the cloud albedo effect, or the indirect climate effect, which has the largest error bar associated with it. So that's really the focus of my work. It's trying to reduce the uncertainties associated with that indirect climate effect. So we've seen this before and probably know about the climate effects of aerosols. But in case you don't, well, just briefly, the direct effect has to do with the direct interactions of the aerosol particles themselves with the radiative balance of the atmosphere. So any kind of aerosol particles can absorb and scatter radiation, and this generally leads to a cooling effect that's fairly uncertain. But even more uncertain is the indirect climate effect, and so that can involve the process of how the aerosol particles take up water and lead to cloud droplets, as well as the resulting effects on the cloud properties, like the radiative properties in the cloud lifetimes. And so that's even more uncertain, is what's going on here. So that's what we're trying to get at here. So I want to start from, I'm a teacher first and foremost. So I want to start from kind of the fundamentals and give you an idea of, what goes into how aerosol particles nucleate cloud droplets. And you guys are probably maybe aware of this, maybe not, but I'm going to try to explain it the best I can. And start simple, right? If we're looking very fundamentally, if you consider just a very pure water droplet, the way that water droplet grows, that's what we're trying to figure out. How does the aerosol particle grow to be large enough to be considered a cloud droplet? It depends on, of course, the atmospheric conditions, so the vapor pressure of water available in the atmosphere, but it also depends on the particle size in terms of the Kelvin effect. So the way I explain this to my undergraduates is that in terms of intermolecular forces, so if you're chemists at all, you learned this in second semester Gen Chem, right? Very small particles have very few water molecules in that particle, and so lower intermolecular forces to hold the water molecules in the particle, and so you have a higher vapor pressure of the gas phase above the particle for very small droplet sizes. And so in this case, you favor evaporation. The particle's not going to grow for the very small particles. But as you get bigger and bigger, you've got more water molecules, stronger intermolecular forces. The water would rather go into the particle. And so you're going to have a vapor pressure lowering effect as the size gets bigger, and it's going to favor condensation and growth. And so this is the Kelvin effect. So the idea here is that particle size, particle curvature is important for CCN activity. And if you know anything about the atmosphere, or anything about water, you're going to say, well, you're never going to find water that's pure, right? That's the best solvent in the world. There's always going to be something dissolved in it, and so there's also this solute effect that kind of competes with what's going on in the pure water droplet. And so, again, this is an intermolecular forces kind of effect. So you've got ion dipole forces that result in interactions that affect how the particle grows. So for smaller and smaller particle sizes, you get higher solute concentrations. Higher solute concentrations favors higher intermolecular forces. You get a vapor pressure lowering effect. And so condensation is favored under these conditions for smaller particles compared to the larger particles. And so you've got these two competing effects that are occurring within a solution droplet in the atmosphere that regulates when you're going to get cloud activation, or whether or not a droplet will grow to be a cloud droplet. And so when we combine these two opposing properties, what you get is this, what we call a Kohler curve. And it represents the equilibrium vapor pressure above a solution droplet. And you can see there's a maximum in that curve, and that's what defines our critical parameters. So you get a critical diameter and a critical saturation ratio. And so this divides this curve up into two different regions. And of course, it's described by traditional Kohler equation. So the AW is the water activity term, so that's that solute effect, and the exponential term is the Kelvin effect. So you add those two together, and you get the Kohler curve. So below that critical diameter, you get a stable region. And in this region, your solution droplet is in stable equilibrium with the water vapor, and we know things tend to roll downhill. So under these conditions, the particle is going to evaporate, it's not going to grow, you're not going to get CCN activation. And it's once you get above these critical parameters, that's when you enter into an unstable region, and the solution droplet's going to grow unconstrained. You're going to get a cloud droplet no matter what under those conditions. So really what we want to get at experimentally in the atmosphere, what are those critical parameters? What's the critical supersaturation, the critical diameter? And so that's what we try to measure experimentally. So this is basic fundamental theory of how a droplet grows, right? And as I mentioned, I'm interested in mineral dust, and it's kind of my first passion. You may say, well, dust is insoluble. You're not going to have a solution droplet. This is a solid particle. And so that kind of has implications for how we theoretically think about how particles will form cloud droplets in the atmosphere. So we have to rethink. Traditional Kohler theory won't work for insoluble particles. And so this is kind of why I'm interested in. Of course, you've got all kinds of different types of components within the mineral dust. I've worked mainly with clays in the past, but I'm interested in mainly because they make up over half the total atmospheric dust mass. They are probably one of the most abundant aerosols found in the atmosphere anywhere. And so we want to know how the dust particles can contribute to cloud formation. We know they're good ice nuclei. How do they contribute to kind of warm cloud formation? And the problem here is that it interacts very differently with water vapor than a solution droplet. Instead of the absorption uptake, you get physical adsorption that occurs. Okay, so that's going to change the way we think about CCN activation of insoluble particles. And just to give you a little history, as of 5-6 years ago, the previous assumption was that mineral dust is never going to contribute to the number of active CCN in the atmosphere unless it's got a substantial amount of soluble material. So freshly emitted dust from the Sahara Desert, for example, would never be considered CCN. And that's because you don't have that water activity term that helps promote condensation. You don't have the soluble component that lowers that vapor pressure. Instead, but you do have wettable particles. We know that these dust particles are wettable in terms of multi-layer water adsorption. So it was previously believed that these are never going to contribute. And this was the assumption up until a couple of years ago. And I just want to show this because this is kind of the first evidence that shows that CCN activity of mineral dust is probably possible under atmospheric conditions, and the fact that pre-adsorbed water on the dust particle in terms of multi-layer water adsorption below 100% relative humidity could contribute to that CCN activities, even if there are no soluble material present. So in 2009, Herrick et al. Put out this paper, and what they did, they came to different conclusions than this, but what they did is they looked at the CCN activity, the measured CCN activity of dust particles, the same exact time of dust particles that were either dry generated or wet generated. So they can generate the aerosols in different ways. They sent them through a dryer, and if you've worked with dust at all forever, you're going to know that it takes a lot longer than the residence time of a diffusion dryer to actually dry these things out. So you're going to still have adsorbed water on the surface on dust particles, even if you send them through the dryer. So you've got wet and dry dust, size select, and then you measure the number that become active CCN and the total number of available particles. And the ratio of the two gives you an idea of the fraction of particles that become CCN active as a function of the saturation ratio. So you can get out these critical saturation ratios from the experimental CCN measurements. It's a very expensive, fairly complicated way to get CCN activities. So experimentally, you get that critical saturation ratio at about 50% of all the aerosol particles that get activated. And so here I show their results, and it's a little busy, so just to make a point, they get basically the same results for all the different types of dust that they studied. But if you look at the 100 nanometer selected dry diameter particles, they've got the critical saturation ratio of the wet generated E-light versus the dry generated E-light. So what this is telling us is that the wet generated E-light, which has a water coating on the dust, has significantly lower critical supersaturation. So it's a more efficient CCN than the dry generated aerosol. This gives us an indication that pre-adsorbed water probably does affect CCN activity. And you kind of think to yourself, well, duh, of course, water on the surface before cloud activation is going to be important for cloud activation. But this actually showed that. And it's because of these results that there have been some advances in the theory. And I'll give you a little bit of a background. Theoretically, what's going on is if you have a dry particle, insoluble dust particle, 0% relative humidity, there's no water. As you increase the relative humidity, you start getting generally a monolayer of water about here at low relative humidities. And then if you continue to increase the relative humidity, you get multi-layer water adsorption. This is a very typical type 2 BET adsorption isotherm that can be easily modeled with a number of different types of multi-layer adsorption models. The model that they use here is the Frenkel, Halsey, and Hill adsorption model, which tends to fit well at high relative humidities, so in this region. And this kind of offsets the fact that you don't have that water activity component, the solute effect that would help increase the ability to form cloud droplets. But then, of course, under supersaturated conditions, you also have that Kelvin effect, that particle curvature effect that still is keeping them from growing, right? So now we can they've modified Kohler theory to combine a multi-layer adsorption model with the Kelvin effect, and they call it the FHH-Adsorption Activation Theory. So this first came out with a paper by Surjama and later with Kumar and the Ninnis group. And it's really quite simple. So this is basically the Kohler theory. You still have the exponential Kelvin term, but instead of the water activity term, they've replaced that with the standard multi-layer adsorption model. A very simple replacement. We're no longer talking about anything that has soluble material. We're talking about freshly emitted mineral dust that is purely insoluble. So I want to basically what you get out of it is very similar to a Kohler curve. You get an activation curve. You can get out the critical parameters to understand a little bit about CCN activities. So I'm going to talk a little bit about that FHH adsorption model and what that means. So this is a standard multi-layer adsorption isotherm and the FHH model. You can fit your experimental adsorption isotherms to this model and get out these fit parameters, the A and B FHH adsorption fit parameters, and you can only get these experimentally. What they mean, or what they mean in terms of what's actually going on, is the A parameter represents the kind of short-range interactions between the mineral surface and that first monomolecular layer of water. And then the B term represents the more long-range van der Waals interactions between the surface and subsequent monolayers of water, so kind of the reach that the mineral surface has in terms of multi-layer adsorption. So you can imagine the A term really kind of helps figure out what the shape of the adsorption isotherm is at low relative humidities, and the B term is more important at higher relative humidities where you have multi-layer water adsorption. So obviously the B term is going to be more important for CCN activity than the A term. But these have to be measured experimentally. You have to be able to have an experimental adsorption isotherm and be able to fit the model to get those. So we can really easily measure water adsorption, and we wanted to find, what's the kind of most wettable, insoluble particle that's out there that's going to be important for the atmosphere. And one of what we came to is, of course, clay minerals. Clays are fairly wettable in terms of mineral dust, a lot more than silica or alumina individually, and they also make up over half the total atmospheric dust mass. So you're still talking about a major component of atmospheric aerosol. In particular, we were interested in the montmorillonite clay and the elite clay, and that's because geologically speaking, they are, geologists called them hydratable clays. So they take up a lot of water compared to other types of insoluble minerals. So we wanted to find something that was insoluble that we knew would get multi-layer water adsorption. And so that's why we chose those two clays to look at. And the way we get our water adsorption measurements is really straightforward. We have a humidification system where we can control the relative humidity by changing the ratio of dry to wet nitrogen. And we can measure the relative humidity in a mixing chamber, and then we flow the humid air over a thin film of our dust sample that's deposited directly onto an infrared internal reflection element. And so we can monitor in the condensed phase the absorption or the uptake of that dust, that water on the dust particles as a function of relative humidity. Of course, we always start out with very dry particles, and increase the relative humidity, and we'll sit on it for a few minutes to make sure that we've reached steady state water adsorption, so we get equilibrium water adsorption measurements at increasing relative humidities. And so this is what our results look like. Very simple for undergraduates to understand this stuff because they learn about infrared fairly quickly, but these are basic infrared spectra. The background here is the dry clay, so everything you see is because of water absorbed directly on the surface. So it's really clear you see the appearance and growth of the water bending mode and the OH stretching mode as you increase relative humidity. And we can apply Beer's law and optical constants for bulk water and get water contents as a function of relative humidity. So we can get these water adsorption isotherms. And the adsorption isotherms have been published previously in Langmuir. So we're now taking these and trying to see what we can do in terms of predicting CCN activities from them. And so these are our adsorption isotherms in terms of coverage versus saturation ratio. The circles are experimental data, and then we have fit the FHH adsorption model to the data, so the solid colored lines is the FHH adsorption model. You can see that it fits pretty well, and we can get out those FHH adsorption parameters, the fit parameters that we can use in the activation model. For comparison, I also include A and B FHH parameters. I've kind of scoured the literature, and I've found two model papers that have tried to incorporate the adsorption activation theory into it. And these are the parameters that they use in those model studies. And fundamentally, they're based on water adsorption measurements of insoluble particles that are not minerals. But in general, the A and B parameters don't vary, have never really varied too much. But we are obviously getting different values than what those models are using. If you take those parameters that the models are using, at least these two models are using, and you plot the adsorption isotherm, you get the dashed line. So we're clearly, the models are under predicting the amount of water that's on the surface under these sub-saturated conditions. And so that's a very significant difference. I just wanted to show that for comparison. Yeah. Yes. Yes. Yeah. So the F in multi. Yeah. Right. So it's very difficult to get anything at 99% relative humidity, right? So in multi-layer water adsorption, you continue to get, at least these models of all show that you continue to get growth of the particle. Yeah. Well, so I believe this more than this kind of downward thing. So this is within the variability of our measurement. And for our system, at about 97% relative humidity, you start to get a little condensation and some cold spots. And so that causes problems. And so we can't measure anything above, we cut it off at 95%. So ideally, you have data points up here that are very close to between 95 and 100% relative humidity to fit these a little better, but this is the best we can do with our system. Yeah, so you get condensation in some issues. There's some uncertainty in the relative humidity measurement that causes problems. Yeah, we're not that precise. But for first approximation, this seems to work pretty well. And I'll show you the results here in just a little bit. But so then we can take our fit parameters, plug them into the FHH activation theory, and get out these activation curves. And so this is just an example of the curves that we get for 200 nanometer dry diameter particles. The E light's in green, more light's kind of pinkish color, and then of course the values that the A and B the models are using are there. So there's very small variability in what those critical parameters look like. So even if there's large variability in those A and B parameters, this seems to be not much sensitivity in terms of that CCN activities. And you'll also notice that this is about 0.3% supersaturation, which is very reasonable for atmospherically relevant conditions. So clearly these values are getting us into conditions where this is very possible to occur in the atmosphere. And of course, we're kind of testing a theory, right? And so we want to be able to compare it to experimental CCN activation measurements, because we're taking bulk water adsorption measurements and applying theory. We want to see how does that compare. And so for 200 nanometer dry diameter particles, this is the critical supersaturation values that we get for our elite and montmorillonite. For the same clays at the same dry diameter, the Kumar et al. Using CCN activation measurements get basically the same exact answer we do. So this is really exciting. It tells us that our CCN activities derived from this combined, bulk water adsorption theoretical approach that we've done very simply agrees very well with CCN activation measurements. So that's a really great result, and we were really excited about that. And it's for the same types of clay particles. So there's one more thing that we can kind of look at this, do with our data to get a little bit more information, and that is to plot the activation curves. This is the critical supersaturation as a function of the dry particle diameter on a log-log plot. So the black lines represent standard hygroscopicity parameters. The kappa value of 0 represents a completely hydrophobic particle. Kappa value of 1 is completely soluble particle. And so you can kind of see there's a range of what hygroscopicity. So we can kind of connect our CCN measurements to the hygroscopicity of the aerosol particles. The major difference that we saw here in terms of what the models are using and what we're using is a change in the slope of this. And so we can look at the slope in terms of the power law exponent. And so we get much lower power law exponents than what people are considering to be fairly normal for these types of particles. And what this actually suggests, and I'm not sure if this is necessarily true or not, since we go kind of a roundabout way to get to the CCN activities, but it suggests a lower sensitivity of the CCN activation to the dry diameter particle. which may actually be true for the insoluble particles, and a greater variability of the hygroscopicity parameter with the dry particle diameter. And that also makes sense because you can think about it in terms of as insoluble particles get smaller and smaller, you get higher and higher surface area to volume ratios. So higher surface area, more water uptake, higher hygroscopicities. So you would expect that hygroscopicity could potentially change with that dry particle diameter. So that makes, at least theoretically, it makes sense. And that's really everything that we've done in the last year or so with this. All of this work is coming out in atmospheric environment very soon, within the next month, hopefully. But just in conclusion, we've used very simple infrared spectroscopic measurements to get water adsorption and use those water adsorption measurements to predict CCN activities, and it works really well. We can understand a little bit about the hygroscopicity of the particles. And of course, what the big piece of this is that it's helping us understand that even freshly emitted mineral dust, dust that has very low soluble components, could potentially contribute to the number of the cloud droplet number concentration in the atmosphere. So it should be, at least on a regional scale, should be considered in atmospheric climate models. So that's my conclusions. Of course, I want to thank my undergraduates for their work. This is Annie Greenaway. She did a lot of the theoretical calculations. Josh Harris did a lot of the experimental work. And Matt Christie's right here. We were at the Elephant Sanctuary in Arkansas. And of course, all the funding for this project. And one more thing I want to talk about, and I have the Hearst Foundation here at the end, and I really need to thank them because they've brought me here today. They've paid for my travel to be here, and it's really more related, linked to this program I'm going to try to develop. The idea, and I've initially called it approach, and that, of course, that name is going to change. We all like acronyms, right? So this is tentatively stands for the Experiences in Professional Research Organizations in Atmospheric Chemistry at Hendrix. So the idea is to get undergraduate students to experience real professional research, professional scientists beyond the walls of more limited resources within a liberal arts undergraduate environment. Students never get to see big research field operations and aircrafts that have all these different instruments on them and things like that. And it's kind of awe-inspiring for them to be able to actually see what's going on in real research labs. And so, get them to observe it and participate in it. And so that's the major aim of the project. I've actually just found out I received funding through an endowed professorship to actually carry this project out starting in the summer of 2015. And so that's when I'll be back here in Boulder with students next time. But that should be when we start this. So right now we're just in development stages. The Hearst Foundation is paying me to be here and help develop the project. And this is kind of an overview of what my initial vision is. I want them to obviously, observe what's going on in maybe national lab, professional lab settings. So you guys here at INCAR and people at NOAA and what goes on in those labs. And that can take on a number of different forms. I could talk about that. I want them to learn about the research. I want it to be an educational experience. There's no standard atmospheric chemistry course at Hendrix, and so they don't really learn about atmospheric chemistry. They don't know the science behind ozone formation in the troposphere, and so having a little bit of a learning component to it. And I want them to actually do some science too. So all of these things together could be very high impact for undergraduate students who are considering going into a science career, research career. So that's kind of the basic idea. And of course, I'm here talking to you guys because it's the development of those undergraduate experiences in the professional research environments that's the hard piece to put together. I can teach them anything, right? But being able to connect and network while I'm here is the important piece. And so that can kind of come in a number of different forms. the more lower impact form would be just touring the national lab facilities, which there's a whole bunch of opportunities around here, right? And just getting them to see what's going on, but a higher impact would actually get to meet the professional scientists one-on-one. Maybe this could be in just a small meeting room discussions with scientists and students, and maybe students can interview scientists or something like that. But even better if they can actually see the scientists in action. And one more high impact thought would be, to shadow a scientist for a morning or an afternoon or a full day or something like that, or being able to see scientists give real research seminars like this, right, if the timing all works out. But those are some of the ideas of this program, and that's kind of what's brought me here today. So I just wanted to give you a little bit of a plug on that and why I'm here and why I'm talking to you, other than that I like to share my research too, but that's the real reason why I'm here. So, and I have my email address and my cell phone number if any of you are interested in this program or have any kind of comments or suggestions or questions about it, or if you think you might be able to help me in any way. I know everyone I've talked to today has been extremely helpful and extremely willing, and I've actually gotten more ideas than I can take on. It's a little overwhelming at this point, but I appreciate your time, and I guess this would probably be a great time for me to take questions, whether it be on my program or my research. And again, thank you for having me and being here this afternoon. I think I left plenty of time.
Okay, just for the sake of recording, I'll pass the mic around. Does anyone have any questions?
So by the way, I think eProach is an awesome acronym. So that's just my vote. I want to ask you about the representativeness question about these dust aerosol. It seems like dust can have a lot of soluble components, which once they're wetted and then re-evaporated can change the nature of the surface of the dust particle and make it into something that suddenly is wettable. And so it goes back to that first experimental arrangement you showed, where they looked at the particles generated with an atomizer versus particles dry generated. It seemed like the atomizer particles would be very different than particles, say, that you've created, where you take a dry particle and you just put humid air over it. Yeah, and I wonder if you can comment on what water processing does to change the whole nature, and then also, this is going to be a big question, also how it relates maybe to the atmosphere, where you have you may have a lot of different components along with the dust, and how truly insoluble are dust aerosol in the atmosphere?
Yeah, you have an excellent question. Of course, it's going to be a hard question for me to answer. But yeah, that was evidently the first conclusion that they came to, is the wet generation technique resulted in kind of a rearrangement of the soluble component to the surface, and then that affected the CCN activity. I've done, I can't necessarily say for what they've done, right? I think they've looked into that. I think that was a big question, and they actually maybe even saw some of that in terms of some potential contamination in their water that they were using or something when they atomized it. We actually wet deposit our dust particles and let it dry, and we've done XPS EDS measurements to look at the surface, the soluble components on the surface before and after wet deposition. We see no difference in the soluble components, at least for our measurements. So that may or may not, I don't think it's happening with our system, but it may actually be happening with theirs, and I think that was one of the big arguments. So I actually reached different conclusions from their measurements than what they did, and that's obviously an issue. And certainly in the atmosphere you can have that happen too, right? And you have soluble material everywhere and all kinds of different aerosol particles. So that's a big issue. The question is how much soluble material is present and how big of an effect does that have on the CCN activity? And the answer, I think, at least for me, is I don't know. But that's kind of the next question. So the Nennis group has modified this adsorption activation theory they now call it the unified adsorption activation theory or something like that, but to reintegrate that soluble component and its effect on the CCN activity. So the next step for me is to actually add some soluble material at various concentrations and using our same measurements, and then applying this newer version of adsorption activation theory to see if we can get CCN activity. So that's our next step. That's the plan. I'm hoping, I've reached out to them, and I'm hoping to actually work together with the NINIS group on this problem. Yeah, it was a really excellent question, though.
Okay, any other questions? I just had a quick question about the eProach stuff. How many students, first of all, and are you aiming at like a specific year, like senior year, or how many do you anticipate bringing in at what level?
I want to kind of keep it open. You know, anyone who's had general chemistry, I can probably explain ozone chemistry to, right? Right now, I have funding to bring at least 4 students in the summer of 2015, and I've got funding to do this twice. So within the next 3 years, 2 cohorts of students. Eventually, the hope is to get other small schools involved, bring in some external funds to help fund the program, and make it kind of bigger, better, badder kind of thing. I think right now, in my budget, I have at least 1.5 to 2 weeks worth of time that we can spend out here. So it's quite a good chunk of time. And they would get graduation credit for participating too.
Okay, thanks again.
Thank you.
Appreciate it.